So that was for simple linear regression. Now let's talk a little bit more about something else. So for multiple linear regression, pretty much is the same. Okay, so what is this? Precisely speaking, we have now again several data points. We get n data points. But for each data point, now we have x1, x2, blah, 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 up to xp. Whenever I write xi and I in the superscript, that means this is a vector. Okay, the first vector, second vector, the ith vector. Okay, so when you see xi, that's a vector. When you see x1, okay, or xi, where I is at the subscript, then this is a scalar. This is a value, a real number. So whenever you see, for example, xij, where I is in the superscript, then j is in the subscript, this means the jth element of the ith vector. Okay, so I hope this is not too confusing for you. So now for each data point, we get p variables or p independent variables. Okay, we want to use that to get some kind of predictor explanatory models to explain the difference in y. So now our straight line becomes some kind of hyperplanes, and we get coefficients alpha as a constant, and the beta 1, beta 2, blah, 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 up to beta p, each one for an independent variable. Okay, so given all of this, we now want to find several variables, and this number now is greater than 2, is p plus 1. We want to find p plus 1 variables to minimize the sum of squared errors. Okay, so that's pretty much all we want to do for multiple regression. If you want to derive a formula for that, you are still able to do that, first order condition, and then you're done. So when we have a summation like this, okay, this is beta 1 times xi1 plus beta 2 times xi2, and so on and so on. We may make it simpler. So we may simply write it as beta transpose xi. So what's this? Beta is a vector, including beta 1, beta 2, beta blah, and the xi is another vector, right? So this is just an inner product. I hope this is reasonable for you. Okay, so this is just a way to solve or to consider linear regression. So we consider linear regression as an optimization problem, as a nonlinear program. Okay, and you may also take other courses like your statistics course, your linear algebra course. There are several other ways to consider your linear regression problem or to derive the formula. Maybe you may see in some textbook that we are actually projecting a vector to a specific vector space, and so on and so on and so on. But anyway, at least now you have one way to explain to yourself why the formula is looked in that way. Also, I want to mention to you one thing is that maybe when you are learning statistics, you have the following question, is that we define the errors as squared errors. Maybe your statistics professors also mentioned this to you, saying that we choose to define the error terms as square terms because you cannot have positive terms and negative terms canceling each other. But if that's the case, actually absolute errors should also make sense, right? We may simply define those errors as alpha plus beta and the difference between that and y, and then we take absolute values. That makes sense, okay? If we formulate our problem like this, the problem makes sense. But the thing is that if you want to solve this problem is more difficult to solve from the perspective of optimization. And pretty much now you have a feeling about why. Because this function cannot be differentiated, right? If you have a square function, you may differentiate it. If you have a kink function like your square absolute value function, it's not so easy to deal with. You may still use your algorithms, whatever, to search for an optimization, but yeah, why do we want to do that? So pretty much that's one reason why people accept this setting, why people accept using square terms to define fitting errors. Lastly, I want to spend a few minutes to talk about some other linear and some other regression models. So one thing is that some of you have learned this in other courses, saying that when we want to apply linear regression to do prediction, and we want to avoid overfitting, then we may do regularization. Well, what's that? The idea is very simple, is that we are given several variables, okay, x1 up to xp, but in many practical applications, the amount of variables that you may obtain in a prediction problem is huge, millions for example, and you have no idea whether one of them is really useful in doing a predictor. So you let the model choose that for you. Among all the variables you get, you don't choose them by yourself. You let the model choose it for you. So how to do that? Basically, you still formulate a least square problem. You still want to choose alpha and beta. Of course, here beta is a vector. You still want to choose alpha and beta to minimize the sum of squared errors. But here you have a lambda as a penalty of using variables, and you plus a penalty term here. Also, the idea kind of is like a Lagrange duality or Lagrange relaxation. But anyway, let's ignore that for a while. This term has some impact. What's that? Basically, it says we want to minimize the sum of everything. So we hope, ideally, all this beta j is 0. Ideally, if you really do beta j setting all of them to be 0, then of course your sum of square error would be large. So you need to carefully choose a subset of beta and make them positive or negative. You need to choose the most effective alpha and most effective beta to make them positive or negative, so that you may minimize the sum of squared error while do not get a too large penalty. Okay, that's indeed an optimization problem, and nonlinear optimization problem, right? You try to get some balance among all possibilities. So when you do this, we call it ridge regression. Or similarly, some people use lasso regression, and the only difference is that here the square term becomes the absolute value function. So I'm not going to go into details about when should you use ridge, when should you use lasso, what's the different properties of the formula you obtain through ridge and lasso. Please refer to other courses. I just want to show you that for these very popular regression models, again, they are unconstrained convex programs, right? You have variables, you don't have constraints. You have a convex term here, another convex term here. That's how you know these problems are solvable. That's how you know formulating a problem like this makes sense, because this model is really useful for you to do something. If you formulate a model that cannot be solved, that is not really useful. That's how we use the optimization perspective to look at ridge and lasso.